Alright, welcome back to the SciMax channel. Today we will continue exploring the use of OpenCode, an AI LLM coding agent for doing things like molecular simulation with the Fairchem UMA models. So Fairchem is a research group out of Meta. They have been collaborating, we've been collaborating with them on making machine learned potentials that are graph neural networks, and the UMA models, Universal Model for Atoms, are the latest and greatest models that cover heterogeneous catalysis, molecules and molecular crystals, inorganic materials, MOFs, and quite a lot more. So this is all open source. You can pip install it. You have to get some access tokens from Hugging Face, but that's all free. You just set up the account and set it up. And what I want to look at today is how something like OpenCode or Claude Code, is what I've used in the past, can help us learn how to use the UMA models. So these are the three tasks that I'm interested in getting done today. First, see what we can learn about the UMA models. Then let's see if we can just do a CO bond length. Maybe these should be one word or two words. And then we'll see if we can get to the CO bond length adsorbed on platinum 111, all driven by natural language. So let me start up OpenCode. OpenCode is like Claude Code, but it's an open source version, and you can make it work with many different models. I'm going to keep working with Claude Sonnet because I like it a lot. And let's go back here and let me copy this. I've been trying to port my Claude Code skills over to OpenCode. So let's see if I can say use the Fairchem skill. And that's just a markdown file somewhere, and it's going to look for it. This is something I have set up, and then it will read it, and that will kind of give it some specific information. See, it's already read the readme.org file. Sometimes these agents, these tools are just so aggressive is the only word. I can say they do more than you ask for that. So let's start with task one there. So I'm just going to tell it to start with task one and tell me what I can do with UMA. Okay, so it is doing some web fetching and learning it. And then it's going to tell us all the kinds of things that it can do, what types of calculations, model variants. That's kind of nice. We have the fastest model, the best model, but it's slower. Things that we can do like this, and there are different tasks that you use for different purposes. So if you want a molecule property, you use OML. Later we want an adsorption property, we'll have to use catalysis. And it's a little bit subtle what you do with the molecule in that case, so we'll see, we're going to see what happens. Okay, so that's helpful. You can ask it all kinds of questions and get into it. Let's see about task two. Explain how we will do task two. Of course, you can make it just do task two, but you don't really know what it's going to do until after it's done. And so here it says we need to set up a geometry, do a geometry optimization. It's recommending we use this faster, smaller model for testing, the bigger model for publication. I think we'll start with the small one. I think that's a good idea. I don't want this to take, it's not going to take very long anyway. For an isolated molecule, you should use OML. And this is a great, bit of information. It's not obvious all the time which one you should use. And here, because we've already informed the model a lot about it, we get exactly what we're supposed to do. Options, use ASE, we'll do that. And then we have these options. Any of these will work fine. I've done this before. And then we need to tell it when to stop the optimization. This is a quite tight convergence level. And then this is probably fine. And it even sets up, here's what the code will do. Let's have a look. Load, attach a calculator. This is just pseudocode. And then what we're going to get is something like this. It gives us an experimental number. And then it gives us some activities we could do after that. All right, we do not have a GPU. I'm running this on a Mac Mini. There is a GPU, but I doubt it's going to, it's not like the regular kind. Have you already logged in and requested? I have done this, so I think that's going to work. And okay, let's do it. Use the smallest model on a CPU, and I would like, well, let's see a plot of the trajectory. And a visualization, really asking for a lot here, of the final geometry. All right, so let's see what happens there. So this should generate a script. That should be no problem. I have an environment variable set for running Hugging Face offline that sometimes causes a problem. So we'll see if that is an issue here. So we've got some, looks like we're making some PNGs. Looks like it's running it there. You can see this popped up, 1.244. Looks pretty reasonable. Here's the energy convergence. I mean, this is like really just amazing. It would take for a long time to code all of this stuff up yourself. That's okay. And now we just get a nice summary here. Including the total energy. Oh, I did say palladium. Okay, well, that was pretty straightforward. Now it's even, thinking ahead on task 3. This is more complicated. We have to build the metal surface slab. We have to put CO somewhere on the surface, and here it knows that we should use OC20 instead of OMO. So let's do it. Let's do task 3. What decisions do I need to make for making the slab? Now I'm curious what it's going to tell me. You have to choose the unit cell size, which it just told me that. 4 atoms is 2 by 2. That's pretty small. It depends on what you're trying to do. And the slab thickness is the other big one. 4 layers is probably good. How big you want it depends on whether you want to account for coverage effects or not. You use a small unit cell if you are interested in coverage, and a large unit cell if you want the low coverage limit. I think we can do 2 by 2. We do also have to figure out what lattice constant we want to use. And I think we'll just use the experimental lattice constant for now. In the past with DFT, you might optimize the bulk to get the right lattice constant that is there, and then use that to construct the slab. So, okay, let's use 2x2 unit cell with 4 layers for the metal slab. And then what about the sights? Where should we put it? Now there's also not a right answer here. You put it where you want. If you want to know on the top, you put it there. If you want to put it on the bridge or the FCC, sometimes you might want to change those. Here it says that based on experimental things, CO prefers the top site. And so I think I agree. Let's use the top site. Okay, so let's do the top site. Put CO. All right. Usually we have another choice to make. What about which layers of the slab to relax? So this is also something in the past you might freeze the bottom layers to constrain them and just relax the top 2 layers. So that's actually recommended. And all right, that sounds pretty reasonable. How do you fix the bottom 2 layers? Okay, so it's just going to use a fix atoms constraint. That also seems pretty reasonable. Okay. Okay, let's set it up. Set that up and run it. That little pitter-pattering is my dog's tail wagging in a dream. He's laying over by the furnace or the radiator, having a good dream. This is what you do when it's building. You wonder, talk to yourself, look at another terminal, answer an email. Okay, so this went by a little bit too fast. It did generate a fancy looking long script, but it has some plot.circle. That's not apparently a real thing, so now it's fixing it. See what happens. This is probably what you might call like the old hallucination problems, except that what's better now is we have an ability to iterate and solve the problems without, my direct intervention. We've been fixing periodic boundary conditions. These are all mistakes that a new person would make on their own. and I actually didn't think to ask about it. Alright, so we got something to work. And we probably should get an image. Let's see if it made one. Open. Is a kind of a funny looking image that I'm a little skeptical of the way it's plotted. So we probably don't actually have a square array. And let's see what we got in our script. So a predictor, that's the small one, CPU, OC20. It's building an FCC 111 slab. It's just the figure is not that good. Let's see, use the ASE view functionality to visualize the relaxed geometry. Alright, so we see on CO Palladium it's gotten a little bit longer. Alright, there is what we have. Now, I'm a little skeptical about this because it looks like the ones with X's are the ones that are frozen. So let's go back here and see what has happened here. So if I had to guess, maybe it mixed up the indexes. So it does use some fixed constraints. If the tag is less than 2. Alright, it's a little bit funny. Great catch. It's maybe not a catch. I could be wrong. Okay, so obviously you're not going to be able to trust that every single thing is done right, just so. I guess I could even see this is tagged 1. 2, 3, and 4. So we probably really wanted to tag things that were 3 and 4. So, alright, so let's see what we have here. Absolutely right to be suspicious. The constraints are backwards. It assigns tag 0. So indeed, the bottom 3 layers are fixed. Alright. Now, that really makes you wonder why that distance is 1.15. I guess that's what it started at. So we have to rerun this. It's kind of okay to figure this out here. That's a mistake that also could have been made. if you just didn't get the greater than or equal to or less than or equal to sign correct. But it gives you an idea of like how specific you need to be and how clear you need to be on telling it what to do. And yeah, this is called sycophancy or something, sycophancy, where it just compliments me. It's also just maybe 2 decades of experience to know that I should look at this geometry and look at it not just by having it make a plot, which was obviously not right in Matplotlib, but using the ASE viewer so that you can see what's happening here. So now you see the x's are down here. This is actually what we intended. These were free, and now we have 1.16, which is a nice result. Okay. All right, I like that. Let's close this and that. Let's go ahead and see if we can get an adsorption energy too. So we need the bare slab, no problem. This is something that's not right though. We can't mix and match OMO. And so I need to tell it this OC, we need an OC20 energy for CO. Okay. While that's going, let's go ahead and look over here. And you can see that we've created like a lot of little artifacts, mostly Python scripts, some data files, trajectory files, including corrected. I don't totally love that. This feels messy, and like even an hour from now might be difficult to go back and figure out like what happened. So maybe we'll ask it and just see what happens. You know, here it's saving a text file, and let's see what we get for an adsorption energy. I don't actually have a reference number to see if it makes sense, but it should be, I guess it will be something like a little negative. All right. Okay. Minus an EV sounds pretty reasonable for this. Seems kind of close to this range, and if you wanted to see how else it works, you might try other other combinations. Seems reasonable. Maybe there's some coverage effects or something else. Let's see, proper constraints. So like if you read through all of these, you can learn quite a bit as it goes. might talk about this context window up here. So according to OpenCode, this has cost us about $3. Um, this is like a real-time cost. There's only one of them, and so even if it costs, like if we kept going for another half hour, we're probably looking at $6-ish, $6 or $7 of cost. I have no idea if this is real cost. You have to eventually go check your API key usage. And if you're logged in or authenticated against a subscription, then it's not even the right number. This is just based on the number of tokens. So if you have a subscription to Claude or Claude Pro or Claude Max, they don't really charge you. They charge you a fixed fee per month, and then you have a certain number of tokens you're allowed to use in a unit of time. Where you might get concerned is if you launch in a parallel process. Say we launched 100 of these agents and had it do 100 different adsorbates, and it took half an hour for each one, then we're suddenly talking about $300. So that's probably not the way you want to do it. You would instead use this kind of framework to generate the scripts that would run those, and then you launch the scripts independently of the LLM. All right, let's see what is happening here. So it's making an index. It has some information about the citations, getting help. This is going in like the README file. Yeah, so it's made a readme.markdown. Let's see what it says over here. That you can use to go back and try to figure out, what was done, what happened, maybe what the critical results are. This is why we can't expect to mix and match these, so we need a consistent energy. And some things about lessons learned, just to remind you, and other details about what we did, even the last date, etc. All right, I think that's probably good for today. We looked at using the Fairchem models and automating, setting up some simple molecular calculations and adsorption calculation. We had to do a little bit of due diligence to check the results, make sure we got what we wanted. We weren't specific enough, or it made a mistake, I don't know. But we got it fixed, and we're able to get some CO adsorption energy on palladium 111. And overall, in half an hour, that's pretty good, since we didn't have to write any code to do that ourselves. We just had to figure it out. So thanks for coming, and hope you come back and check it out again later. See you next time.